Washington University in St. Louis came up with an air monitor that can detect COVID-19 virus variants in about 5 minutes. This right here is a proof of concept device that was built by this team. While this is still a proof of concept, let's critically analyze their biosensor through published studies and consider the real-world applications for this. We're going to look at this paper here that is on the biosensor, in addition to the supplemental material that comes along with it. Currently, they're calling this a PAC, a proof of concept pathogen air quality device for monitoring in real time, with a 5-minute time resolution of direct detection of COVID aerosols, which is just free-floating COVID in the air. The device sensitivity is okay between 77 and 83%, with a limit of detection between 7 and 35 viral RNA copies per meter cubed. It's important to note that this is dependent on the COVID variant. How it works is that ambient air is sucked into the device using a vacuum air pump, which pulls air in at a high velocity of 66 meters per second, which is about 150 miles per hour. 10 meters cubed of room air is being sucked in during these 5 minutes. For a relative scale, this is what 10 cubic meters looks like. And then this air cyclones as it is pulled in, where the virus particles are caught in the liquid layer here. This solution is then passed across a microimmunoelectrode biosensor, an MIE. Essentially, they're just measuring the change in current across this electrode that everything is plated on. The electrode itself is plated with nanobodies that are from llamas. And these llama nanobodies can adhere to the spike protein of COVID, and it's set a certain distance so that the interaction between the free-floating tyrosine amino acids with the spike protein itself causes electrons to be released, so an electric charge is released that can be then conducted and measured through that electrode itself. And this is how they tell if there is COVID being detected or not. So now that we know how it works, let's talk about how it functions. This PAC monitor is supposed to be set up about 4.5 feet off the ground within a small enclosed room. When it's first set up, it needs 5 minutes of virus-free control air to set the current at, which is easy enough because you can just aerosolize PBS for 5 minutes. So you can just sit there with a little PBS mister, and this will create if there are virus particles in the air, to fall and away from the device and just give you a natural control. And after this initial 5-minute sample control, you can set it to sample continuously for a user-defined number of loops. The nice thing is that once you have that initial control reading, while the MIE chip lasts for 70 sample scans, this is only 35 real-time sample measurement because you have to do 35 baseline scans, which means that there's actually 10 minutes between each real-time scan and that the device can last for about 6 hours. Now let's talk about the lower limit of detection, the least amount of virus that the PAC monitor is able to detect. This is highly variant dependent, where Delta is the most sensitive and this Washington or Omicron variants are the least sensitive. So let's look at that another way. Our wet cyclone here is our PAC monitor, so it's these ones right here, and we have low, medium, and high detection. So being below our detection limit between 10 and 30 would be around this region. So over here, that would be the same as about right here as the lower detection limit. So now that we know it can detect virus, let's see what it means in terms of RNA copies per milliliter. Well, they had 2 volunteers that lived in small apartments that had the Delta strain, specifically the BA.5 strain. These were asymptomatic individuals, so a low detection of virus particles would be present, and they had air collection when they had virus shedding while they were asymptomatic, and also when they had negative PCR tests down here. These volunteers stood at least 2 feet away from the wet cyclone inlet, the PAC monitor, and after 5 minutes of sample collection, took syringes and took samples out of the sample collection to be tested at a lab. And these individuals had detections of around 33 and 34 CT value. So for reference, greater than 36 CT means COVID is not detectable. This would be a negative PCR reading. Between 30 and 36 would be a weakly positive. And then less than 30 would be a definite COVID positive for the PCR test. The qPCR standard curve generates the CT value. Now, when they're having this 33 to 34, so we'll just give it a 30 to 35 range, they're around this area right here. So this would be between 10 to the 1 and 10 to the 2 COVID viral particles per milliliter. So if we recall, that 10 to the 1 to the 10 to the 2 would be right here, which is within our detection limit. So even if you're a asymptomatic individual with low viral shedding, this device will detect it, which is fantastic. Now that we know how the sensor works, let's talk about some of the drawbacks of the current proof of concept, as well as how it could be used conceptually in the next video.